this isn't really about so much about theory. It is about proving scalability for bare metal Kubernetes in a completely simulated environment. And we are going to talk about what we built, how it works, what we learned, and how, let's say, you can also do it using open source tools. So a bit of a background. I am Kashif Khan. I am a maintainer of this project called metalcube.io. I'm also a co-chair of the CNCF technical advisory group called TAG Infrastructure. I'm working as an open source architect at Ericsson Software Technology in Finland. And as you can see, my work lives at the intersection of bare metal Kubernetes and open source governance, basically taking physical infrastructure and machines and making them behave like cloud native objects or resources. And I'm passionate about bringing or bridging the gap in between hardware level control and Kubernetes automation. So first of all, a bit of a motivation, like why did we do this? And the most important answer in this case is scalability matters. If you're running Kubernetes on bare metal at let's say enterprise scale, you want to know that this tool, for example, Metal3, can it handle hundreds or even thousands of clusters? The problem is that when we test this real hardware, or we want to test the scalability, it comes with a cost because these are expensive. So that's why we turned into simulations inspired by one of the famous tools of OpenStack called OpenStack Ironix Fake Driver. We build fake components that mimic the behavior of the real hardware so that we can test, stress, and validate the Metal3's control plane at scale without, let's say, spinning up a single real node. Now, just to clarify, when I am saying fake in this rest of the presentation, it doesn't mean that we are like it's a mocked shortcut. These are fully behavioral simulations that exercises the same APIs and same workflows as real deployments. A bit of a background and also like showing you the Metal3 stack. So just for the context, how many of you are aware about cluster API or Metal3? All right, I would say almost half or less than half. So I'll just anyhow briefly introduce the stack itself. At the top, we have Cluster API, which is the standard declarative framework for creating, automating, managing the lifecycle of clusters. We have a provider for that inside Metal3, which is the Cluster API provider Metal3, which is then integrating with components inside Metal3 like bare metal operator, and also bare metal operator talks, as I said in the previous slide, with OpenStack Ironix, which is the actual engine that is, let's say, handling the provisioning, inspection, and all the things that we would want to do on top of a bare metal server. Think of Metal3, let's say, or this component as one of the cloud providers for your physical hosts. And together they turn this bare metal into a Kubernetes native abstraction. You describe your infrastructure that you have here in YAML, and then there are controllers in Metal3 that will take care of making it real inside the Kubernetes cluster. So now, as I said, that Metal3 leverages Cluster API, which is a SIG cluster lifecycle project. It is like where you can create and maintain your clusters with self-hosted and self-managed environments. You start with a management cluster, and that cluster has controllers that create a target cluster for you, which themselves can become management cluster for or even more clusters, or they can even be your workload cluster. And cluster API comes with controllers which can orchestrate thousands of let's say hundreds of these other clusters. And the most powerful tool, first of all, that Cluster API gives you is the provider spec. You can actually deploy a cluster using Cluster API on top of, let's say, GCP, on top of AWS, Azure, all the public clouds that you name it, they have their APIs and providers which you can use to deploy a cluster using cluster API on these public clouds. But when it comes to bare metal, there was none previous to Metal3 was introduced. There are now a few more which are also providing you to deploy your clusters on top of bare metal, but Metal3 was one of the forerunners, I would say, in that sense, and it allows, or it gives you an API to represent your bare metal server inside Kubernetes. And then, as I showed in the previous Metal3 stack, it has a provider that provides or allows you to have a management cluster that you have deployed using clustered API to manage on top of your bare metal server. So Metal3 has been incubated recently. It is a CNCF incubating project, which of course signals both maturity and community adoption. It is self-managed, self-hosted, and acts as an infrastructure provider for cluster API. Just as I said, you would see like CAPI that is known as like provider for AWS, or CAPI for Azure. And the difference is that instead of cloud VMs, Metal3 provisions physical servers. And it does that using Kubernetes native APIs, which means it fits naturally into the cloud native ecosystems, like you can use GitOps, operators, CI/CDs, all of it. So the basic idea is that you have a bunch of servers and then you want to deploy Kubernetes cluster. And how do you do that? You first actually represent your server inside Kubernetes using a declarative API, which I would be actually using these words bare metal host a lot during this presentation. So bare metal host is kind of like a representation of the server inside Kubernetes. So, and this is a portion of how the YAML looks like. The most important things that you would need to give for Kubernetes, or let's say Metal3 controller, to make it work is the baseboard management controller, or the BMC addresses, and the boot MAC address, and then also the name of the BMC secret. And this is then the prerequisite that Metal3 would require you to give before it can really act on this bare metal server. And this is the representation of the bare metal server inside Kubernetes. Before I jump in, one of the key components, before I jump into the mainly scalability issue, I just wanted to introduce the bare metal operator just for the context. So it is one of the key components in Metal3. We call it BMO, or bare metal operator, and this operator manages the life cycle of the bare metal host resources. So that YAML that I actually showed you previously, that is the bare metal host custom resource, and bare metal host custom resource is then reconciled using this operator, and it talks to Ironic. So in Metal3, like, although I'm saying that it's an OpenStack Ironic, but you don't need to deploy the Ironic yourself. It comes as packaged within Metal3. So once you are deploying the bare metal operator and the Metal3, it will actually be also deployed. And Ironic is then the instrument which is talking directly with your server. It is doing, hardware introspection. It can provision, it can deprovision, and it can maintain the life cycle of your bare metal server with constant reconciliation. In short, BMO is what makes the physical servers behave like cloud native resource driven entirely by Kubernetes CRDs. And I want to also introduce a few of the components I am going to also talk about in the next few slides. For example, this deploy RAM disk. This is also a very important part when it comes to the provisioning lifecycle. We call it Ironic Python agent. It acts so that when you are first booting up using, let's say, PXE booting, then this deploy RAM disk is actually running on top of your server. It does all of this introspection and stuff that I just mentioned. And it also then, if you are, let's say, provisioning a host operating system on top of your bare metal server, it copies that host operating system into one of your local disks. And once the host operating system is then deployed, it actually reboots the server with that operating system and then runs the cloud init and all the stuff that you would need inside to make that bare metal server a Kubernetes node. All right, I would just first want to show a short demo. This is pre-recorded. There is like how we are doing or handling all of these things in our CI. So although I'm saying that it is all bare metal server, but in our CI, when we are testing using virtual machines. But when we are testing using virtual machines, we don't use which commands, for example, to power on, power off, or provision anything. We use Kubernetes APIs. We use kubectl commands, and that's what I'm going to show. And when we are using these kubectl commands, Metal3 APIs are talking to these virtual machines using virtual BMCs. So everything that you see, the workflow is the same as it would happen on a bare metal server. So before I actually just show you few things to notice. So this is actually the simple script. It has, I don't know if it is visible that much, but it has like 2 or 3 commands. One is the stop VM, and as you can see, when I would be running this function, what it does is that it has currently deployed 2 bare metal hosts here on the top left, which are in the available state, and the online status is true. That means they are currently running in a running state. And these are the Virsh VMs that I'm just like showing for the purpose that we are not touching anything on the Virsh level, but you can see that the VMs are running. And here the commands are, let's say, start VM. What it's doing is that it's patching this node's online status to like true, and then the stop VM will patch this online status to false. So the idea is that when I am actually calling the start VM function, or let's say now currently it's running, so if I call the stop VM function, it should take the status to false, and then the controller, the bare metal operator, would make sure that the VMs are closed, and all of these things are done via virtual BMCs and Ironic. So yeah. So now I have like this, the demo, in this demo, I have called the stop function, and you can see that it has been patched to false. And then you will see that, yeah, so now the VMs are now starting to shut off. So this is how we are actually testing the Metal3 in the CI. And similarly, when I am calling the start VM, it will actually start running the VMs, and you will also see that this is actually the serial logs. The PXE booting has started on the VMs, and as you can see, this is actually the logs from the booting that deploy RAM disk or Ironic Python agent. So these are real VMs when these are deployed. Let's say when these are provisioned with operating systems, you would be getting, let's say, a Kubernetes control plane in these VMs, and then you can also deploy your workloads and test all the stuff that you would do inside a Kubernetes cluster, let's say. And this is actually the big picture of the workflow. The workflow starts with that the user is providing the cluster templates, and then we have controllers that I showed, like cluster API and cluster API provider Metal3. It tries to find and associate a bare metal host if it is available. Once it finds, it actually then, let's say, gives the desired state. Let's say I want to provision this bare metal host with this image, and this is the Kubernetes version that I want on top of it. Once you have given the desired node state, bare metal operator, the operator which was reconciling the bare metal host, talks with Ironic and gives, Ironic is the one which is then giving these baseboard management controller or BMC level commands. And then it is through the sushi tools, it's actually booting the IPA, and this is the node. So once it boots IPA, it asks to boot, let's say, as I said, it copies first the OS image, and then once it is done, it asks it to reboot from the OS image and run the cloud in it. And there are some commands then back and forth in between Ironic and IPA just to make sure that Ironic has asked it to provision the node, if the node is provisioned or not. Once the node is provisioned, through the cloud init, a Kubernetes API server is initialized, and then cluster API also makes some queries back and forth to make sure that the cluster is ready, and then reports back the same status to the user. Now, what we want to really scale test in this scenario is that how these components are behaving when we have, let's say, hundreds or even thousands of clusters. So how can cluster API and cluster API provider Metal3 or bare metal operator or Ironic handle this type of load when you have thousands of nodes or hundreds of nodes inside your cluster? Now, I would first also tell you what is the challenge if we don't simulate. So, few words that I have already mentioned, but I want to reiterate about this Ironic Python agent is that it is one of the heartbeat of the provisioning cycle. It is a lightweight Python service running in a RAM disk, and it on each bare metal node. That is one of the important thing to notice, that this IPA would need to run on each bare metal node. It is responsible for inspecting hardware, for deploying operating system image, as I said, setting up the bootloaders, for example, and continuously hard beating to Ironic to tell that, okay, I am alive and I am working and everything is actually going well on this bare metal server. And then Metal3 relies on this Ironic Python agent, or in short what we call IPA, for every hands-on operation. But there is a challenge. And the challenge is that when you, as I said, it is actually running on each bare metal hosts, and when you have n number of nodes, this would actually require quite a lot of resources. For a ballpark number, when an IPA is running, let's say it would require 1 to 2 virtual CPUs and half of your RAM, because it actually considers the half of the RAM as its own memory, and then it will give back the other half for the, let's say, other tasks of the, let's say, what the kernel is running for the operating system and loading and those kind of things. So it is considerable amount of resources. I can, let's say, a ballpark number would be 1 to 2 virtual CPU and, let's say, 4 gigabytes of RAM. And when you multiply that with hundreds or even thousands, that is the number then you need if you want to scale test really, if these components that I just showed are able to work with it. So the first challenge was to actually how we can manage this amount of resources when we are doing the scale test. And this is a simple example of when we are doing the tests in our CI. So those VMs that I showed a while ago, VM1, VM2, a typical number for those would be 2 virtual CPUs, 4 gigabytes of RAM, and 50 GB of disk each. And then this is, let's say, when we are deploying 4 bare metal hosts for a let's say 3 control plane worker scenario in some of our tests, we require almost 8 vCPUs, 32 GB of RAM, and 300 GB of disks. So our objective was to actually, as I said previously, test controller scalability, how many bare metal hosts can, let's say, BMO or bare metal operator can reconcile concurrently, the API responsiveness of Kubernetes API, if can Kubernetes API servers handle the volume, and of course the Ironic throughput, that is, can it handle thousands of provisioning requests in flight. We are not, let's say, testing disks or PXEs here. We are just testing the orchestration capability of these components. And what is really consuming resources are these node components that mainly, as I showed with the numbers, that when you scale, it requires huge amount of resources. So what we did is to take out the, let's say, Ironic Python agent, and we deployed a fake IPA, as we call it. It emulates the real agent lifecycle, but it is just a server running with all the APIs that Ironic talks to IPA, and it is actually replying back to Ironic that, yeah, everything is healthy. You don't need to worry about this node. So it sends the heartbeat, it gives the inspection results, it gives the provisioning status, and it does all of it in memory. The fake agent allows to have the same protocol as the real ones. So from Ironic's perspective, when Ironic is actually talking with this, Ironic is not able to identify if this is a real Ironic Python agent running or some server just responding to the API calls that it was making. So in the Ironic's world, it is talking to, when I'm deploying 500 nodes, it is talking with 500 real nodes. That means we can safely push Ironic and BMO to their limit without frying any real servers. But there was still a missing piece, and that was the Kubernetes API server. Now, as we know that Kubernetes API server, when it comes up, it also consumes resources because it needs to run kubelet, and then it needs to at least have the etcds and those kind of things. And we still wanted to make sure that we even can we actually push it to the boundary that we can also fake those API server responses. And that's when we came up with the fake API server idea, and this was vastly motivated by a tool that is in Cluster API called Cluster API in-memory provider. What it does is that when we are actually combining this fake IPA and fake Kubernetes API server, which we call FCAS, this is just a pod running. Whenever we want to actually deploy a Kubernetes API server, we make a query to FCAS pod that, hey, I want to deploy a Kubernetes API server, give me an API endpoint, so that I can talk, like that can behave as one of the API server, but then it just gives us the API, the IP address of the API and the port, and that's it. There is no real actually kubelet or anything running. Whenever we are making any queries towards that, the FCAS pod makes sure that the API calls are then again redirected and telling, and so the whole simulation environment thinks that it is actually talking with a real Kubernetes API server. And together with FCAS and fake IPA, it allows us to then run end-to-end Metal Cube workflow, simulating thousands of nodes and cluster, because as if you remember that these were the components we were mainly interested to scale. We faked the other components which were really taking up resources. But we still made it in a way that these components don't even understand or know that they are not talking with real Kubernetes API server or the real Ironic Python agent on the node side. Now I'm going to just show a small demo. I have screwed up, by the way. I wanted to show a live demo, and in this scenario, I don't have 1,000 clusters, but I was able to reach at least 500. Let's hope that the cluster is still alive. Okay. I think API, yep, 10 minutes is good enough for me. So, okay. Let me first fix the connectivity. All right. Okay, is the font good, big enough? Oh, I'm not showing the correct screen. Wait. How can I mirror? Or maybe I can just put it here and stand here so that it's visible. It's interesting. I have to probably mirror the display. Just a second, another technical glitch. No. Seems that I'm not able to find the mirror space. Yep. And yep, I think this is good. This is now too small for me to even okay. Is the font big enough? Can you see it from the back? All right. A bit bigger, okay. Good, okay. So wanted to show you first what do I have in this cluster. So this is actually a Kubernetes, it's a mini cube running. So if you remember the picture where I showed, there is a cluster API management cluster. So in this case, Minikube is the cluster API management cluster where I deploy all the cluster API and cluster API provider, Metal Cube and bare metal operator, all of these components first. And these are the lists. So as you can see, there is one bare metal operator, and we are deploying a couple of Ironic pods. Then we have deployed some common pods for Ironic, like and then MariaDB. There is this cluster API provider, KubeStep provider, KubeADM Bootstrap provider, KubeADM control plane controller, the basic core controller for cluster API. We have few Metal3 components, cluster API provider, Metal3 controller, IP address manager controller, and this is the bare metal operator controller manager. And we have this FCAS pod that I was talking about, which is mimicking the Kubernetes API server. And the fake EPAs are running here as container tools. So 10 of them for this demo. And as you can see from the names, okay, maybe a bit easy to read if I just reduce the size a bit. So 10 fake EPAs from 1 to 10, and then corresponding sushi tool for each EPA, which is then talking to the virtual BMC controllers. So if I show you how many of the bare metal hosts I have here, sorry, I missed the namespace. So 501, and all of them, if I now just remove the number and show you the status of each, they are all provisioned. And then I am going to show you kube serial get clusters -a, and I have also 500 clusters. Let me just sort it out. Here, as you can see, there are 500 clusters running, and so cluster API thinks that there are 500 clusters. Bare metal host thinks that, or bare metal operator is reconciling 500 bare metal servers. So, and the same goes for all the components that we wanted to stress test. So, machine is an object that is taken care of by cluster API controller. So I can show you how many machines do we have. 501, and if you see, if I show you the machine name, and you can see that they are all in a running state with the provider ID, provider ID is provided by the, when a Kubernetes API server is running on top of one node. So all of them are actually having one of the provider IDs. So cluster API is also scale tested. Same goes for cluster API provider Metal3. So if I want to check a Metal3 machine and see how many of the Metal3 machines do we have. So 500 Metal3 machines. And one last thing that I would probably want to show is the Ironic, how is it behaving, and let me quickly go inside. And I'm now talking with the Ironic endpoint, and then I'm trying to know if Ironic is aware that there are these many nodes, so that this also can show that if Ironic is dealing with, and as you can see, Ironic also is dealing with these all 500 nodes that I just showed in the real picture. So this was the way we are, and this is, by the way, 16 core 20, or if I remember, 32 GB 300 or 500 gigabytes of disks VM where I'm running this, and there are still resources. So probably if I show you, so this is not at all killing most of the resources. So let's go back to the presentation again, and let me first I guess I would have few more minutes, so as soon as yeah. So the learnings and takeaways, first of all, the scaling test helped us redesign the ironic deployment at scale. So I showed you that there were 2 ironics, but in the normal scenario when we are having only 2 or 4 BMHs, there was only 1. So that's how we knew that we need more ironics and we need to break out this vertical deployment into pieces. And that's how I showed you that there were actually 3 different ironic deployments now, one with the 3 ports, one with the common, and one with the database, the MariaDB. The suggestion would be plan first of all what to scale and what can be faked, and then components that you are scaling shouldn't be aware about faking. As you just saw, the components that you are scaling, they were not aware in this test that they are talking with like simulated components, and faking also comes with a cost. For example, we needed to have 10 EPA, fake EPAs, for example, in this one. And when we are going to thousands, it would require more containers to run. So it will at least consume some basic resources, but not at the scale what we just saw in the beginning of the presentation. And here I have at least some blog posts that we have in Metal3 if you want to try it out and check how this all works. These are the links here. You would find it in the blog post in the Metal3 project. Thanks a lot. I hope it was interesting to you, and if I have any time for questions, I'm ready to take in.